Okay, guys, in this video, we are going to take a look at independent events. Definition: two events are independent if the occurrence of one of them has nothing to do with the occurrence or probability of the other one. And the definition says that probability of A given B is just going to be probability of A. And similarly, probability of B given A will just be probability of B. So what's going on here? So if you look at this side, you are saying A and B are independent. So whether you give me B or not makes no difference on A. So we can just cross this out, and this is just going to be probability of A. Okay, and probability of B given A will be the same. I don't care. B doesn't care about A, so this can be crossed out, and then you're just going to get probability of B. All right. Okay. Now, events are going to be dependent if they are not independent. So just to give you an example, let's imagine that A is the probability that it'll rain in Miami, Florida, and B is the probability it'll rain in Tokyo. Is it going to be independent or dependent? Well, let's say I told you it'll rain in Tokyo today. Is that going to affect the chance that it'll rain in Miami? Well, no, because these cities are so far away, then these two events are independent. But if I gave you, let's say A is the event that it'll rain in Miami, and B is the event it'll rain in Hollywood, Florida. Now, because these two are so close to each other, the fact that if I told you it'll rain in Miami, that is actually going to increase the chance that it'll rain in Hollywood, Florida, because these are close to each other, right? And if there is a big front, it's going to cover both of them, right? So these are not going to be independent. Now, one thing that people a lot of times mix up is the idea of independent versus mutually exclusive events. These are not the same thing. So just to give you two examples, let's say example one is that Mary will pass a quiz, and F is that Jack will pass the same quiz. Now, if they don't help each other, these two events are going to be independent, right? There's not going to be a chance that Mary will pass the quiz. That's not going to increase just because Jack passes it, right? But so they're independent, but are they mutually exclusive? Well, no. Is it possible for both of them to solve the quiz at the same time? Well, yes. So these are not mutually exclusive because mutually exclusive events cannot happen at the same time. That's not happening here. Now, if I give you another example, example number two, where Mary will pass the quiz and F will be Mary will not pass the quiz. Now, these two events are not happening at the same time, right? Because if she passes, it's not possible that she doesn't, right? So these events are mutually exclusive. However, they're not independent. Why? Well, if I told you, for example, that Mary passed the quiz, that is going to affect the chance that she will not, because now the chance that she will not is going to be 0 because you know that she passed it. So these are not independent. So just don't think that these two things are the same thing. All right, now in our all problem solving, instead of using the definition of conditional probability, we're going to use something called multiplication rule. It is actually much easier to check when you are trying to figure out if two events are independent or not. So this rule belongs on your note card. I don't want you to necessarily memorize it, but you need to know it. So two events are independent if probability of E and F, so E and F happening at the same time, equal probability of E multiplied by probability of F. Now, word of caution, this rule does not work all the time. If your two events are not independent, it's not going to work. So don't just always think, oh, now there is a quick and easy way to find probability of E and F. I'm just going to multiply them. Well, you can do that, but they have to tell you that the two events are independent. And if they didn't tell you that, then you cannot use this rule. Okay, so first example, suppose probability of E is 0.3 and probability of F is 0.5. We know that E and F are independent. Well, if we know they're independent, then the E and F probability is just going to be, according to our test for independence, probability of E multiplied by probability of F. So all we have to do is just multiply these two numbers to find probability of E and F happening. So 0.3 times 0.5, that's going to give me 0.15. right? All right, now suppose they ask us what's probability of E or F. Now this is where you have to use what we call additive rule. What was it saying? Anytime you see this or thing, oops, this one, or, you know you're supposed to use additive rule. So this is going to be probability of E plus probability of F minus probability of E and F. This rule, by the way, works all the time, regardless of it's independent, not independent, doesn't matter. It's a general rule. Now, probability of E was 0.3. Probability of F was 0.5, right? We were given that, and we just in the previous part found probability of E and F using the test for independence. So we're going to subtract the intersection, and we're going to get 0.65 for E or F. All right, the next example, let's say A is the chance that a student is going to take a math class, and B is a student is going to take a science class. Are these two events going to be independent or not? Well, this is what we are given. Probability of A is 0.6, probability of B is 0.5, and probability of the intersection or that they're happening at the same time is 0.3. So we just have to check the test for independence. So this is called multiplication rule or test for independence. Now we're given all the parts. Probability of A and B, that's 0.3. Is that probability of A multiplied by probability of B? Well, 0.6 multiplied by 0.5 is 0.3. So both of the sides are just 0.3. 0.3 is equal to 0.3, and that means that they're independent. Now, I want to go back really quick to the question we looked at before, which is the table question. Okay, so let's go back to that question. So this was a question where we were saying social media user was one of the events, and we found that the chance of social media user is 0.638. Okay, that's social media user. Okay, so and that's what we found before, so I'm not going to repeat it. The next one that we found was that the respondent was young, 18 to 34 years old. So we found that to be 0.283. Okay, and then on the next slide we found the end probability that a respondent is an 18 34-year-old and also social media user. So we found that by looking at the overlap, and that was 0.221. Now, question, are these two events S and A1, are they independent or not? Well, we're going to just use test for independence. So if they are independent, that if I multiply each individual probability, it should give me the intersection. Now, it's actually better to use fractions, but in this case, I'm just going to use decimal places, decimals, because it gives me the answers in decimals. So this is going to be 0.180554, and that is not the same thing as 0.221. So these events are not independent. But just to think about that, why they're not independent. If I told you that somebody 18 is 18 to 34-year-old, is that going to affect you knowing that that person will use social media? Well, yes. If a person is young, he or she is more likely to use social media. So the last example we're going to look at, the last example is going to be, let's scroll through this one, another table example. So this one is a little bit different. Here, your shoe size, whether your shoe size is 9 or less, and whether you prefer summer as your favorite season. We want to know whether these two events are independent, okay? So do you think your shoe size has anything to do with your favorite season? Well, it doesn't look like it. I don't think so. So probably these two events are going to be independent. But let's check it out. So if they are independent, then test for independence must happen, right? What is the test for independence? Well, it's going to be probability of A multiplied by probability of B equal to probability of A and B. So let's compute each one. A is going to be that the shoe size is at most 9. Okay, so this is my A. Okay, what is the shoe size at most 9? Well, that's going to be 40 divided by 100, right? Because everybody whose size is at most 9 are sitting here. So this would be 40 divided by 100, which is going to be 0.4. Now, B is going to be the event that you prefer summer as a season. Okay, so what is summer? Well, summer is over here. So what's the chance of summer? Well, that would be 60 divided by 100, and that's equal to 0.6. Now, is that equal to probability of both? Right? So probability of both, is that equal or not? Well, what does it mean both? That's and probability. So remember, and both in probability theory are really the same thing. Okay, so what does both mean? Well, somebody has to have a shoe size at most 9, and at the same time, the somebody should like summer. So that would be these 24 people. So we're going to take 24 divided by 100. Well, that's going to be 0.24. Okay, now is 0.4 multiplied by 0.6 equal to 0.24? Yes or no? Well, we can multiply them. You should maybe know that the 4 times 6 is 24. So 0.4 times 0.6 is going to be 0.24. Check. So that means that these two events are going to be independent.